There is a star in our galaxy that, if placed where our sun is right now, would swallow Mercury, Venus, Earth, Mars, the entire asteroid belt, Jupiter, and reach the orbit of Saturn. Not metaphorically, not approximately, literally. The surface of this star would extend to roughly 9 astronomical units from the center, roughly where Saturn orbits. Everything inside that radius, every planet, every moon, every asteroid, every spacecraft we have ever launched, every piece of matter in the entire inner solar system would be submerged inside the body of a single star. This star exists. It is in our galaxy. Astronomers have measured it, debated it, and as of 2024, confirmed it as one of the strongest candidates for the largest reliably measured star ever found. And it is not the only one. The universe produces objects so extreme, so far beyond any intuitive scale, that comparing them to anything familiar requires stepping back again and finding new reference points, because the old ones keep disappearing inside the star. This is the story of the largest stars in the universe. Not just a list of sizes. The full story, how these objects form, why they grow so large, why the largest ones are always the most unstable, how astronomers measure objects so enormous and so distant that the measurements themselves are a story worth telling, and what the current science says about how large a star can actually get before physics itself draws a line. And that line, it turns out, is exactly where things get most interesting. Before we can understand why some stars grow to unimaginable sizes, we need to understand what a star actually is. Not the poetic version, the physical version. Because everything that follows, every measurement, every comparison, every reason why some stars balloon to 1,000 times the size of others, flows from the same fundamental physics. A star is a gravitational engine fighting itself. At the moment a star forms, when a cloud of gas and dust collapses under its own gravity, when the infalling material becomes dense enough and hot enough for nuclear fusion to ignite in the core, two forces come into balance. Gravity pulls inward, trying to compress everything into the smallest possible volume. The energy released by nuclear fusion pushes outward, resisting the compression, holding the star up against its own weight. This balance, called hydrostatic equilibrium, is what defines a star. It is what separates a star from a gas cloud that collapsed but never ignited, and from a stellar remnant that has used up all its fuel and collapsed into a neutron star or a black hole. As long as the balance holds, the star burns steadily, radiating heat and light into the surrounding space. The sun is a perfect example of this balance in action. At the center of the sun, temperatures reach approximately 15 million degrees Celsius and pressures reach 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, hydrogen nuclei, protons, collide with enough energy to overcome their electromagnetic repulsion and fuse into helium. This process, the proton-proton chain, releases energy in the form of photons and neutrinos. The photons work their way outward through the dense solar interior over thousands of years, bouncing and being absorbed and re-emitted, gradually diffusing outward until they reach the surface and escape as sunlight. The sun converts approximately 600 million tons of hydrogen into helium every second. Of that 600 million tons, about 4 million tons are converted directly into energy, mass becoming energy according to Einstein's famous equation. The rest becomes helium, accumulating in the core as the hydrogen fuel is gradually depleted. This process has been running for approximately 4.6 billion years. The sun is roughly halfway through its expected main sequence lifetime of 10 billion years. It will continue burning hydrogen for another 5 billion years before the hydrogen in its core runs out and the physics of its final stages begin. All of this, the temperature, the pressure, the energy production rate, the lifetime, is determined by one thing above all others: the mass. Mass is the master variable of stellar physics. Everything else follows from it. A more massive star has stronger gravity, requiring higher core temperatures and pressures to maintain the balance. Higher temperatures mean faster nuclear reactions, which means more energy output, which means the star burns through its fuel faster. A star 10 times the mass of the sun burns through its hydrogen not in 10 billion years, but in roughly 30 million. It burns 10 times the mass of fuel in roughly 300 times less time. Mass also determines what a star looks like. More massive stars are hotter at the surface, which makes them bluer. Less massive stars are cooler, which makes them redder. And mass determines what happens at the end, whether the star becomes a white dwarf, a neutron star, or a black hole. The more massive the star, the more violent and extreme the ending. And mass determines size, but not in the way you might expect. The largest stars in the universe are not the most massive. This is one of the more counterintuitive facts in all of stellar physics, and it is the key to understanding why the record holders we are about to discuss are so extreme. The largest stars by physical size are not the young, hot, massive stars that dominate the upper reaches of the stellar mass function. Those stars, the O-type supergiants, the Wolf-Rayet stars, the luminous blue variables, are certainly massive, but their sizes are modest compared to what a star can become later in its life. The largest stars by physical size are red supergiants. Old, cool, enormous, and unstable. Stars that were born as moderately massive main sequence stars, typically between 10 and 40 times the mass of the Sun, and then, as their hydrogen fuel was exhausted, expanded dramatically. Here is what happens. When a massive star exhausts the hydrogen in its core, the core contracts. As it contracts under gravity, it heats. The heat ignites hydrogen burning in a shell surrounding the core. This shell burning produces more energy than the core burning did, and that extra energy causes the outer layers of the star to expand dramatically. Not by a small amount. The outer layers of a star undergoing this transition can expand by a factor of hundreds. The star that was perhaps 5 to 10 times the radius of the Sun as a main sequence star becomes hundreds or even 1,000 times the radius of the Sun as a red supergiant. The surface temperature drops dramatically as the radius increases. The same energy output spread over a much larger surface area means each square meter of surface is cooler and therefore redder. The star transitions from a hot blue-white main sequence star to a cool red supergiant. This is the phase during which stars reach their maximum physical size. Not their maximum luminosity. More massive, hotter stars are far more luminous. But their maximum radius. The red supergiant phase is when a star is physically, spatially enormous. And it is a phase that does not last long. By stellar standards, the red supergiant phase is brief, tens of thousands to a few 100,000 years for the most extreme cases. The star is burning through heavier and heavier elements in its core, moving through the nuclear binding energy curve toward iron, and when the iron core forms, the end comes quickly. So the record holders for physical size are inherently transient. They exist briefly, burn brightly in an astronomical sense, and then either collapse or explode. Finding them requires looking at the right moment in their evolutionary history, and studying them accurately requires overcoming a set of measurement challenges that have repeatedly revised the standings. Let's talk about how you measure a star's size, because without understanding the measurement process, the size comparisons that follow are just numbers without context. The direct measurement of a star's angular diameter, how wide it appears in the sky, is extraordinarily difficult. Even the nearest stars are so far away that the angular diameter of their disks is measured in milliarcseconds, fractions of thousandths of a degree. To put this in perspective, the full moon has an angular diameter of about half a degree. Resolving the disk of a star requires an angular resolution thousands of times finer than what the naked eye can achieve. For a handful of the closest and largest red supergiants, Betelgeuse being the most famous, space-based and ground-based interferometric techniques have been used to directly resolve the stellar disk. Interferometry, combining the light from multiple telescopes separated by large distances, achieves angular resolutions far beyond what any single telescope can manage. The Very Large Telescope Interferometer in Chile has been used to resolve the disks of several nearby supergiants with this technique. But for most stars, including the current record contenders which lie thousands of light years away, direct angular diameter measurement is not currently possible with available technology. Instead, astronomers use an indirect method based on well-established physics. The Stefan Boltzmann law relates the luminosity of a star, its total energy output per second, to its surface temperature and its radius. If you know two of these three quantities, you can calculate the third. Specifically, if you measure the luminosity and the temperature, you can calculate the radius. Luminosity is measured by combining the observed brightness of the star, how bright it appears from Earth, with the distance to the star. Distance is where things get complicated. Until recently, stellar distances were measured using a combination of techniques that introduced significant uncertainties. Parallax, the apparent shift in a star's position as Earth orbits the Sun, which can be converted to distance through simple geometry, works well for relatively nearby stars but becomes increasingly uncertain for stars at distances of thousands of light years. For more distant stars, astronomers relied on spectroscopic distance estimates, measuring the star's type and luminosity class from its spectrum and comparing to known standards. These indirect distance estimates carry larger uncertainties. The Gaia satellite, launched by the European Space Agency in 2013, revolutionized the measurement of stellar distances. Gaia measures stellar positions with extraordinary precision, better than 1 microarcsecond in many cases, enabling parallax measurements for stars across a much larger volume of the galaxy than had previously been possible. The Gaia data releases have revised the distances, and therefore the inferred sizes, of many famous large stars. In some cases dramatically. The story of how Gaia revised the size estimates of some of the most famous record holders is one of the most instructive examples in recent astronomy of how careful measurement changes science. A twofold change in distance estimate produces a fourfold change in inferred luminosity, which in turn changes the inferred radius. Size estimates that had stood for decades were revised, in some cases halved, by the application of more precise distance data. This is not a failure of science. It is science working correctly. The measurements became more precise and the models were updated accordingly. With that context established, let's go through the largest known stars from well-established to the current record contenders, always keeping the solar system as our reference. Let's start with our own sun, because every comparison that follows needs a foundation. The Sun's radius is approximately 696,000 kilometers. If you placed a hollow sphere the size of the Sun at the center of the solar system, the Earth would orbit well inside it. Earth's orbit has a radius of about 150 million kilometers, roughly 215 times the Sun's radius. The entire orbital path of Mercury, the innermost planet, lies within about 80 solar radii. Mercury orbits at a distance of roughly 58 million kilometers from the Sun, which is about 83 solar radii. This is the baseline, 1 solar radius. Everything that follows is measured in multiples of this. The Sun is not small by human standards. If you hollowed it out, you could fit approximately 1.3 million Earths inside it. It contains 99.86% of all the mass in the solar system, all the planets, all the moons, all the asteroids, all the comets, all the dust. Everything else combined is less than 0.2% of the Sun's mass. And against the stars we are about to discuss, the Sun is essentially a point. The first star that begins to make the solar system feel smaller is Sirius. Sirius, the brightest star in the night sky as seen from Earth, is not a red supergiant. It is a hot, luminous blue-white star, a spectral type A star on the main sequence. Its radius is approximately 1.7 times the Sun's radius. By the standards of what follows, this is negligible. But Sirius is worth mentioning because of the contrast it provides. Sirius is one of the most visually striking stars in the sky, brilliant, dominant, the anchor of the winter sky in the northern hemisphere. And it is only 1.7 times the size of the Sun. The stars that we are going to discuss shortly are not 1.7 times the size of the Sun. They are not 10 times, not 50 times, not 100 times. They are hundreds and, in the most extreme cases, over 1,000 times the size of the Sun. The scale difference between the most familiar bright star in the sky and the largest known stars is so extreme that no single comparison can capture it. Moving up the scale, we come to the class of stars known as blue supergiants. These are among the most luminous stars in the galaxy. burning with intensities of hundreds of thousands or millions of times the sun's luminosity. But their sizes, while impressive, are modest compared to what red supergiants achieve. Rigel, the brightest star in the constellation Orion and one of the most luminous stars visible to the naked eye, is a blue supergiant with a radius of approximately 78 times the sun's radius. If Rigel were placed at the center of our solar system, its surface would extend roughly 78 solar radii outward, well inside Mercury's orbit, but already large enough that Mercury's orbit would be entirely contained within the stellar atmosphere. Rigel shines with approximately 120,000 times the luminosity of the sun. It is one of the most powerful stars in the local part of the galaxy. But 78 solar radii is, against the giants we are approaching, still small. The blue supergiant Deneb, the tail star of Cygnus, the Swan, has been measured at approximately 200 times the solar radius, depending on the distance estimate used. Deneb is one of the more uncertain cases in the nearby stellar catalog. Its distance has been difficult to pin down precisely, and different measurement techniques give different answers. But whether it is 200 or somewhat larger, Deneb at maximum extent would engulf most of Mercury's orbit. These blue supergiants, however, are not where the size records live. They are extraordinarily luminous and extraordinarily massive, but their high temperatures keep them relatively compact compared to what happens when a massive star cools and expands. The real size records belong to the red supergiants. Antares is perhaps the most famous red supergiant visible to the naked eye from Earth. Its name, in Greek, means rival of Mars, so named because its red color and brightness rival the red planet. It is the brightest star in the constellation Scorpius and one of the most visually striking stars in the sky on summer evenings. Antares has a radius of approximately 680 to 700 times the radius of the Sun. This single number deserves some time to settle. If Antares were placed at the center of our solar system, if the Sun were somehow replaced by Antares overnight, the surface of the star would extend outward to a radius of roughly 680 times the distance between the Earth and the Sun. Mercury, orbiting at 83 solar radii, would be deep inside the star. Venus, orbiting at about 155 solar radii, would be inside the star. Earth, orbiting at about 215 solar radii, would be inside the star. Mars, orbiting at about 325 solar radii, would be inside the star. The asteroid belt, which occupies a broad band between about 330 and 480 solar radii, would be partially inside the star and partially in the stellar atmosphere. Jupiter orbits at approximately 1,100 solar radii. At 680 solar radii, the surface of Antares would sit about halfway between the asteroid belt and Jupiter's orbit. Antares is approximately 550 light-years from Earth. It is a relatively nearby red supergiant, which is part of why it is so well studied. Its mass is estimated at approximately 12 times the mass of the Sun. Not extreme by stellar mass standards, but sufficient to have evolved through its main sequence and expanded into the red supergiant phase. Antares is also a binary system. Orbiting it at a distance of several hundred astronomical units is a hot blue companion star, Antares B. When observed in the right conditions, the companion appears as a tiny blue-green point nestled in the red glow of its enormous companion. The contrast in size is staggering. A star that would be impressive in its own right, rendered essentially invisible by the overwhelming scale of its companion. Antares is nearing the end of its life. Its core is burning through progressively heavier elements. At some point, possibly within the next 100,000 years, possibly much sooner, the iron core will form, the equilibrium will break, and Antares will collapse and explode as a supernova. From Earth, that event will be visible in daylight, bright enough to cast shadows at night, the most spectacular astronomical event in the recorded history of our species. But at 680 solar radii, Antares is not even close to the record. Moving outward in size, we encounter a star with one of the most evocative nicknames in all of astronomy. Mu Cephei is known as the Garnet Star, named by William Herschel, the great 18th century astronomer, for its deep, rich red color. It sits in the constellation Cepheus and can be seen with the naked eye under good conditions. glowing with that distinctive crimson hue that signals a cool, extremely luminous surface. Mu Cephei has a surface temperature of approximately 3,750 Kelvin, much cooler than the Sun's 5,778 Kelvin. Despite this low surface temperature, it shines with a luminosity of more than 100,000 times the Sun. This apparent paradox, cool surface but enormous total output, is resolved by its enormous size. A vast surface area, even at low temperature, radiates enormous total power. The radius of Mu Cephei is approximately 1,000 times the Sun's radius. 1,000 solar radii. At 1,000 solar radii, the surface of Mu Cephei would reach beyond Mars and well into the asteroid belt if placed at the center of our solar system. Mars orbits at roughly 325 solar radii. The inner edge of the asteroid belt is at approximately 330 solar radii. Jupiter orbits at approximately 1,100 solar radii. Mu Cephei at 1,000 solar radii would have its surface extending almost to Jupiter's orbit. Almost every rocky body in the solar system, Mercury, Venus, Earth, Mars, and the inner asteroid belt, would be submerged inside this star. Mu Cephei is a semi-regular variable star. Its brightness changes over time, not with the perfect clockwork regularity of some variable types, but with a rough pattern that repeats over periods of hundreds of days. This variability reflects real changes in the star's size and temperature, the outer layers pulsating, expanding, and contracting as the balance between energy output and the star's gravity shifts. Like Antares, Mu Cephei is nearing the end of its life. Its mass, approximately 25 times the Sun's mass, is large enough that it will almost certainly end in a core collapse supernova, leaving behind a neutron star or black hole. The exact timing is uncertain, but by stellar standards, it is in its final stages. And Mu Cephei at 1,000 solar radii is still not the largest. At 1,000 solar radii, the solar system as we normally conceive it, the rocky inner planets, the asteroid belt, the familiar landscape of our cosmic neighborhood, has largely disappeared inside a single star. Now we go further. For many years, a star designated VY Canis Majoris held a strong claim on the title of the largest known star. VY Canis Majoris, located approximately 3,900 light-years from Earth in the constellation Canis Major, is a red hypergiant, a category beyond even the red supergiants in terms of luminosity and extreme behavior. Unlike the more modest Antares or Mu Cephei, VY Canis Majoris is not a straightforward case of a massive star that expanded quietly into a large sphere of gas. It is one of the most chaotic, turbulent, and extreme stellar environments known. Early measurements of VY Canis Majoris placed its radius at approximately 1,400 to 1,500 solar radii. Later estimates pushed this higher, to perhaps 1,800 or even 2,100 solar radii in some analyses. The uncertainty was large, driven by the difficulty of measuring the star's distance and by the extreme complexity of its environment. If VY Canis Majoris were placed at the center of our solar system at its larger estimates, its surface would extend past Jupiter's orbit and approach Saturn's. Jupiter orbits at approximately 1,100 solar radii. Saturn orbits at approximately 2,000 solar radii. But VY Canis Majoris is not a passive, spherical object sitting quietly at these enormous dimensions. Observations from the Hubble Space Telescope and other instruments have revealed a turbulent circumstellar environment unlike almost anything else in the galaxy. The star is surrounded by an asymmetric nebula of gas and dust that it has ejected over its lifetime, jets and clumps and arcs of material hurled outward in all directions, not in the smooth, symmetric stellar wind of a more ordinary giant, but in violent, directionally asymmetric mass ejection events. Astronomers studying the structure of this circumstellar material have found multiple distinct knots and arcs of ejected gas, each apparently produced by separate mass ejection events at different points in the star's history. The mass loss rate of VY Canis Majoris is estimated at approximately 1 solar mass every 1,000 years. Over the course of its red hypergiant phase, it has shed many solar masses of material into the surrounding space. The star is, in a very real sense, slowly destroying itself, losing mass faster than most stars can gain it. This extreme mass loss has created the complex nebula visible around the star and has also reduced the star's mass significantly from what it was on the main sequence. The current mass of VY Canis Majoris is estimated at approximately 17 solar masses, far less than the 30 to 40 solar masses it likely began with. The lost mass is now distributed through the surrounding space in the chaotic nebular structure that makes this star so visually distinctive. However, the size measurements of VY Canis Majoris have been substantially revised downward by more recent analyses. A careful reanalysis accounting for the complex circumstellar dust that obscures the stellar surface found that earlier measurements had systematically overestimated the angular size by including emission from the surrounding dust rather than the stellar photosphere alone. Current best estimates place VY Canis Majoris at roughly 1,400 to 1,420 solar radii, still an enormous star, but considerably smaller than the legendary estimates that once made it the undisputed record holder. VY Canis Majoris illustrates a fundamental challenge in stellar astronomy. When a star is surrounded by complex circumstellar dust and gas, measuring the actual stellar surface rather than the surrounding material is extremely difficult. The photosphere, the visible surface of the star, is not always where it appears to be when the surrounding material is dense and complex. Separating the stellar emission from the circumstellar emission requires careful multi-wavelength analysis and, in the most extreme cases, interferometric techniques that are only now becoming available. At 1,420 solar radii, VY Canis Majoris' surface, if placed at the center of our solar system, would extend just past Jupiter's orbit. The gas giant itself would be partially engulfed, but it is not the largest measured. Here we need to discuss a star that held the top position for many years and whose case remains one of the most instructive examples of how size measurements can mislead. UY Scuti, located in the constellation Scutum, approximately 5,000 to 9,500 light-years from Earth depending on the measurement, was for a time presented in popular science as the largest known star, with measurements placing its radius at approximately 1,700 solar radii. These measurements, combined with the impressive comparison to the size of the solar system, made UY Scuti famous. Videos and articles featuring UY Scuti's size relative to the solar system were shared millions of times. The problem was the distance. UY Scuti lies in a direction through the Milky Way that is heavily obscured by interstellar dust. The dust absorbs and scatters the light from the star before it reaches Earth, making the star appear dimmer than it actually is and complicating the measurement of its true luminosity. The dust also makes spectroscopic measurements of the star's temperature more uncertain because the dust affects different wavelengths of light differently. Early measurements of UY Scuti's distance placed it at approximately 9,500 light-years, based on its membership in an open cluster and spectroscopic analysis. Combined with estimates of its temperature and luminosity, these distance estimates gave a radius of approximately 1,700 solar radii. Then the Gaia satellite arrived. Gaia's precise parallax measurements placed UY Scuti at a significantly shorter distance, approximately 5,900 light-years rather than 9,500. This revised distance, when propagated through the calculations, dramatically reduced the inferred luminosity and therefore the inferred radius. The current best estimate for UY Scuti's radius, based on Gaia distance data, is approximately 990 to 1,000 solar radii. Still an enormous star. Still a radius that would consume the inner solar system and reach deep into the asteroid belt, but approximately 40% smaller than the legendary measurements suggested. UY Scuti did not shrink. The measurements became more accurate. This is one of the most important lessons from the recent history of stellar size measurement. The stars we are discussing lie thousands of light-years away, behind dust that dims and reddens their light, in crowded stellar fields that complicate spectroscopic analysis. The famous size comparisons that circulate online are often based on the largest estimates in the literature, which are frequently revised downward as more precise data becomes available. The honest picture is this: we know approximately how large these stars are. We know the order of magnitude, but the specific numbers carry uncertainties of tens to hundreds of solar radii, and those uncertainties matter when claims about the record holder are being made. With that caveat clearly established, let's now turn to the current strongest candidates. In the constellation Scutum, in the same general region of the galaxy as UY Scuti, sits a star with the catalog designation Stephenson 2-18. For several years, this star has been prominent in popular discussions of stellar sizes, with measurements suggesting a radius exceeding 2,000 solar radii. If accurate, this would be an extraordinary result. At 2,000 solar radii, the surface of Stephenson 2-18 would extend to approximately the orbit of Saturn, roughly 9.5 astronomical units from the center, or about 2,000 solar radii. The entire inner solar system, the asteroid belt, and the orbit of Jupiter would all be interior to the stellar surface. But here is the fundamental problem with Stephenson 2-18. The star is thought to be a member of a young open cluster called Stephenson 2, located approximately 18,000 to 20,000 light-years from Earth. If Stephenson 2-18 is indeed a member of this cluster, then the cluster's distance can be used to infer the star's distance, and from the distance plus luminosity measurements, the radius can be calculated. The problem is that Stephenson 2-18 may not actually be a member of that cluster. Radial velocity measurements of how fast the star is moving toward or away from Earth, have produced results that are inconsistent with cluster membership in some analyses. If the star is not at the cluster's distance, but is instead a field star at a different distance, the entire size calculation changes. Additionally, if the luminosity implied by the 20,000 light-year distance is taken at face value, Stephenson 2-18 would be one of the most luminous stars in the galaxy, so luminous that it sits at the edge of what stellar evolution models permit for a star of its type. Some analyses suggest the luminosity is so extreme that the stellar classification becomes problematic. The situation is genuinely unresolved. Some data support cluster membership and therefore the extreme size estimate. Other data suggest the star may be a background field giant at a different distance. Until a definitive distance measurement is available, possibly from future Gaia data releases or from new spectroscopic campaigns, Stephenson 2-18's claim to the largest star title cannot be confirmed with confidence. This is not unusual in astronomy. Extraordinary claims require extraordinary evidence. The more extreme the measurement, the more carefully it must be checked. And Stephenson 2-18's measurement depends on a distance that remains contested. Now let's talk about the discovery that has generated the most serious scientific excitement in this field in recent years. The star-designated RSGC 1F01, located in a young red supergiant cluster called RSGC-1 in the inner galaxy. RSGC-1 was identified in the early 2000s as a young, massive stellar cluster embedded in the dust of the inner Milky Way. It lies approximately 6,000 to 7,000 light-years from Earth, in a heavily obscured region that requires infrared observations to study properly. The cluster contains a significant population of red supergiants, large, luminous, evolved massive stars, which makes it one of the richest collections of such objects known in the galaxy. In 2024, astronomers using the Atacama Large Millimeter Array and infrared telescopes published detailed observations of one of the most extreme members of this cluster, designated RSGC 1F01, or simply F01 in some publications. The observations, conducted at multiple wavelengths and analyzed using the Stefan-Boltzmann law applied to careful luminosity and temperature measurements, produced a radius estimate of approximately 1,500 solar radii. What makes RSGC 1F01 significant is not just the size, though at 1,500 solar radii it would rank among the largest stars reliably measured, but the quality of the measurement. Unlike Stephenson 2-18, whose distance is contested, the distance to RSGC-1 is established through multiple independent methods. The cluster's distance has been measured through kinematic analysis, comparing the motions of stars in the cluster with the expected rotation of the Milky Way, through photometric analysis of the cluster's red supergiant population, and through parallax measurements of associated masers. These different methods converge on a consistent distance estimate, giving the astronomical community confidence that the cluster's distance is well established. And unlike VY Canis Majoris, whose measurements are complicated by complex circumstellar dust and asymmetric mass ejection, RSGC-1F01's size estimate is based on multi-wavelength photometry that carefully accounts for the interstellar and circumstellar reddening along the line of sight. The analysis team applied extinction corrections derived from multiple wavelengths to produce a robust luminosity estimate, and from that luminosity, combined with the spectroscopic temperature, calculated the radius. At 1,500 solar radii, the surface of RSGC-1F01, if placed at the center of our solar system, would extend just past Jupiter's orbit. Jupiter orbits at approximately 1,100 solar radii. At 1,500 solar radii, the surface of the star would sit roughly 400 solar radii beyond Jupiter, in the region between Jupiter and Saturn. The gas giant itself would be submerged inside the star. The volume of RSGC-1F01 at this radius is approximately 3.4 billion times the volume of the Sun. 3.4 billion solar volumes in one star. This is currently one of the most credible measurements of an extreme stellar radius in the literature. It does not have the contested distance issues of Stephenson 2 to 18. It does not have the complex circumstellar contamination issues of VY Canis Majoris. It is based on observations at multiple wavelengths with careful treatment of extinction. And it lives in a well-characterized cluster with a well-established distance. As of 2024, RSGC-1F01 stands as one of the strongest candidates for the largest reliably measured star in the Milky Way. But let's be careful about what this means, because the phrase largest reliably measured is doing a lot of work, and the distinction matters. There is a difference between the largest star we have measured with confidence and the largest star that exists. The Milky Way contains approximately 200 to 400 billion stars. Of these, the fraction that are red supergiants at their maximum extent at any given moment is tiny, perhaps 1 in a million, perhaps less. The red supergiant phase is brief, the stars that undergo it are rare, and the chance of a given star being at its maximum extent at the moment we observe it is small. The searches for large red supergiants have been conducted primarily in the solar neighborhood and in a handful of well-studied young stellar clusters. The inner galaxy, the dense stellar regions toward the galactic center, remains incompletely surveyed, obscured by the same dust that makes studies of the galactic plane so difficult. There are almost certainly red supergiants in the Milky Way that are as large as RSGC-1F01 or larger that we have not yet found. They may sit behind dust clouds that have not been penetrated by current infrared surveys. They may be in stellar clusters that have not yet been systematically analyzed for their largest members. They may be isolated field stars without the cluster membership that provides a distance anchor. The record, in other words, is almost certainly not the actual maximum. It is the maximum among the stars we have been able to measure reliably. And the theoretical maximum, the limit imposed by physics rather than observational incompleteness, is something we can calculate approximately. Stellar evolution models predict that red supergiants should not exceed approximately 1,500 to 1,800 solar radii under normal conditions. This limit arises from a combination of factors related to the dynamics of very large stellar envelopes. When a star's envelope expands to very large radii, the outer layers become very loosely bound. The gravity at the stellar surface is extremely weak, a consequence of the enormous distance from the center and the modest mass of the outer envelope. Under these conditions, radiation pressure from the stellar interior can drive mass loss at extremely high rates, stripping the outer layers away. The mass loss strips the star down to a smaller radius. The equilibrium between expansion and mass loss limits how large a red supergiant can get. For stars of typical red supergiant masses, this equilibrium tends to cap the radius at around 1,000 to 1,500 solar radii. Stars more massive than the typical red supergiant range may become hypergiants, objects on the borderline between red supergiants and the most massive stellar types, where the mass loss is so extreme that the star cannot maintain a stable red supergiant configuration for long. These stars may oscillate between different spectral types as their mass loss varies, appearing as red hypergiants, then yellow hypergiants, then losing enough mass to return to a hotter configuration. The theoretical prediction that red supergiants should not exceed approximately 1,500 to 1,800 solar radii is consistent with the observational record. Stephenson 2/18 disputed measurement of over 2,000 solar radii would violate this prediction if taken at face value, which is part of why its distance and classification are contested. RSGC 1F01 at approximately 1,500 solar radii sits right at the theoretical limit. It is not obviously impossible, but it is also not comfortably below the limit. Whether stellar evolution models are correct about this maximum, or whether conditions in specific environments can produce stars significantly larger, is an open question. It is the kind of question that can only be resolved with better observations of more extreme stellar environments, and those observations are now becoming possible with the instrumentation available in the 2020s. Let's step back from the specific numbers and think about what the largest stars in the universe reveal about how extreme the universe's physical processes can be. A star with a radius of 1,500 times the Sun's radius has a volume approximately 3.4 billion times the Sun's volume. If you could somehow fill this volume with material at the Sun's average density, you would have 3.4 billion solar masses, far more than any star could ever accumulate. But the mass of RSGC 1F01 is not 3.4 billion solar masses. It is approximately 15 to 20 solar masses. This means the average density of a large red supergiant is extraordinarily low, far lower than the Sun's average density of about 1.4 grams per cubic centimeter. The outer layers of a star like RSGC 1F01 have densities so low, perhaps 1/1,000,000th or less of the density of the air you are breathing, that they are, in a physical sense, more vacuum than substance. The word surface, applied to these objects, loses its ordinary meaning. There is no sharp boundary between the star and the surrounding space. The density of the stellar atmosphere simply decreases with increasing distance from the center, gradually transitioning from the denser inner regions to the thin outer atmosphere to the even thinner circumstellar wind. Where the star ends is a matter of definition as much as measurement. This is partly why the sizes of red supergiants are uncertain in a way that the sizes of more compact stars are not. The photosphere, the layer at which the star becomes opaque to radiation and which therefore defines the visible surface, is not a sharp boundary. It is a zone of changing opacity, and its location depends on the wavelength at which you observe and on the current state of the stellar atmosphere, which for variable stars changes over time. When astronomers say a red supergiant has a radius of 1,500 solar radii, they mean the photospheric radius at a specific wavelength under conditions at the time of measurement. This number is real and meaningful, but it should not be imagined as the radius of a solid sphere with a sharp edge. The star is more like a vast, diffuse, slowly moving sea of gas, hot and dense at the center, increasingly tenuous toward the outside, with no clear boundary between inside and outside, but rather a continuous gradient from stellar interior to stellar atmosphere to circumstellar material to interstellar space. There is something worth understanding about where these giants sit in the larger context of stellar populations in the Milky Way. Of the approximately 200 to 400 billion stars in the Milky Way, the overwhelming majority are small, dim, cool red dwarf stars. These are stars with masses between about 8 and 50% of the Sun's mass, luminosities tiny fractions of the Sun's output, and lifetimes measured in tens to hundreds of billions of years, far longer than the current age of the universe. The stars we have been discussing, the red supergiants with masses 10 to 30 times the Sun's, represent a tiny fraction of the total stellar population. Perhaps one star in tens of thousands or one in 100,000 is in the red supergiant phase at any given moment. And the extreme objects at the top of the size scale, the stars approaching 1,000, 1,200, 1,500 solar radii, are rarer still. They represent the most massive stars in the red supergiant phase, the ones that began with the most mass and are now near the end of the most extreme stellar lives the galaxy routinely produces. These stars are extraordinarily bright for their brief lives. A star like RSGC 1F01 with a luminosity of perhaps 100,000 to 300,000 times the sun's output, is radiating energy at a rate that would exhaust the energy budget of the solar system in geologically trivial times. The sun will burn steadily for 10 billion years. A star this luminous burns through its fuel on timescales of millions of years. And the red supergiant phase itself is brief within that already brief stellar lifetime. Perhaps a few 100,000 years at most for the most extreme cases. The star spends millions of years on the main sequence as a hot blue star, then expands into the red supergiant phase, then either explodes as a supernova or, in some cases, contracts back to a hotter configuration before eventually exploding. We observe these stars during that brief red supergiant window. The fact that we can find them at all is a function of their extreme brightness. They are so luminous that they are visible at enormous distances, even through the dust that obscures most of the galactic plane. But the sample we have is incomplete, and the true size distribution of the largest red supergiants in the Milky Way remains poorly constrained. Let's talk about what happens when these giants die. Because the death of a star this large is one of the most energetic events the universe produces, and understanding what happens when a star reaches these extreme sizes is part of understanding why extreme sizes are inherently unstable. 4 stars in the red supergiant range, masses roughly 10 to 30 solar masses. The eventual fate is a core collapse supernova. The carbon-oxygen core that forms after helium burning continues to be compressed and heated, igniting successive shells of burning heavier elements, carbon, neon, oxygen, silicon, until an iron core forms in the center. Iron, as discussed earlier, cannot release energy through fusion. The iron core accumulates until it reaches the Chandrasekhar mass limit, approximately 1.4 solar masses, at which point electron degeneracy pressure can no longer support it against gravity. The core collapses in less than a second, reaching densities comparable to atomic nuclei. The infalling outer layers bounce off the rigid neutron core and produce a shock wave that blasts the outer stellar material into space. The result is a supernova, one of the most energetic events in the universe, briefly outshining the entire galaxy. For the largest red supergiants, the explosion is not guaranteed to be straightforward. Some theoretical models suggest that very massive stellar cores with more than 2 to 3 times the sun's mass, may not produce a successful supernova but instead collapse directly to a black hole. The shockwave fails to reverse the infall and the entire star, or most of it, disappears into the black hole with little or no optical display. This is called a failed supernova or a direct collapse black hole event. Evidence for such events has been found in surveys searching for massive stars that simply disappear, going from a detected luminous red supergiant to undetected in a matter of months, with no corresponding supernova. The largest, most massive red supergiants may thus not go out in a dramatic explosion. They may simply cease to exist, the star present one decade and gone the next, leaving a black hole and no visible remnant. Whether this fate applies to stars like RSGC-1 F01 depends on its final core mass, which is uncertain. The boundary between stars that produce successful supernovae and those that collapse directly to black holes is not sharply defined and depends on the complex physics of the explosion mechanism, the structure of the progenitor star, and the properties of the dense matter at nuclear densities. What is certain is that these stars are transient. They will not last. The extreme conditions that make them record holders, the vast radius, the low surface gravity, the extreme mass loss, are also what ensures their rapid evolution toward a violent end. The largest stars in the universe are the ones closest to dying. Now let's go beyond our own galaxy. The Milky Way is one galaxy among approximately 2 trillion in the observable universe. Each of those galaxies contains its own population of stars, its own massive star-forming regions, its own red supergiants in various stages of their evolution. In nearby galaxies, the Large and Small Magellanic Clouds, Andromeda, Triangulum, the other members of the Local Group, astronomers have identified populations of red supergiants and are beginning to study the most extreme members. The Large Magellanic Cloud, a satellite galaxy of the Milky Way approximately 160,000 light-years away, contains one of the most well-studied populations of massive stars outside our own galaxy. The famous star WHG 64, located in the Large Magellanic Cloud, has been measured with interferometric techniques and found to have a radius of approximately 1,500 solar radii, comparable to RSGC 1F01 and among the largest stars reliably measured anywhere. WHG 64 is surrounded by a dense torus of dust and gas that it has ejected, similar in some ways to the circumstellar environment of VY Canis Majoris, but with the advantage that the distance to the Large Magellanic Cloud is very well established. We know it to within a few percent, removing one of the major sources of uncertainty in stellar size measurements. The fact that the largest stars in the Large Magellanic Cloud appear to reach similar sizes to the largest stars in the Milky Way is consistent with theoretical predictions. The maximum size of a red supergiant depends primarily on the stellar mass and the physics of stellar envelopes, not on the specific galaxy. Stars with similar masses should reach similar maximum radii regardless of which galaxy they formed in. In principle, galaxies with higher rates of massive star formation, such as starburst galaxies that are undergoing intense bursts of star formation triggered by mergers or other interactions, might contain larger populations of extreme red supergiants and therefore a higher probability of finding the most extreme individual cases. But the distance to starburst galaxies makes measuring individual stellar radii extremely challenging. The record for the largest star we know of with high confidence is currently held between RSGC 1F01 and WHG 64, both at approximately 1,500 solar radii. The theoretical maximum from stellar evolution models is approximately 1,500 to 1,800 solar radii. We appear to be observing stars at or near the physical limit of how large a stable red supergiant can become. Whether the next generation of instruments will find a star that exceeds this limit, that pushes into territory where the theoretical maximum would need to be revised, is one of the more intriguing open questions in observational stellar astronomy. Here is a question that the size comparisons make vivid, but that deserves its own careful consideration. If you were somehow transported to the surface of one of these giant stars, to the photospheric layer of a star 1,500 times the sun's radius, what would you experience? The surface gravity would be extraordinarily weak. At 1,500 solar radii from a center containing perhaps 15 solar masses, the surface gravity would be roughly 15 divided by 1,500 squared times the sun's surface gravity, about 1/10,000th of the sun's surface gravity. The sun's surface gravity is already modest, about 28 times Earth's surface gravity. 1/10,000th of that is an extraordinarily tiny gravitational acceleration. In practical terms, this means that the outer layers of these stars are barely held. The radiation pressure from the stellar interior, which in an ordinary star is much weaker than the gravitational pressure from the mass above, is here comparable to or exceeding the gravitational pressure. The outer layers float, held loosely, subject to being blown away by the smallest additional push from a stronger radiation burst or a convective instability in the interior. This extreme looseness of the outer envelope is why these stars lose mass at such high rates. The stellar wind, the continuous outflow of material from the stellar surface, carries enormous amounts of mass away every year because the material is so weakly bound. The convective cells in the photosphere of a red supergiant are themselves giants by solar standards. In the Sun, convective cells, the granules visible on the solar surface, are approximately 1,000 kilometers across. In a red supergiant, convective cells can be a significant fraction of the stellar radius itself, hundreds of millions of kilometers across. A single convective cell on the surface of a large red supergiant would dwarf the entire inner solar system. Direct imaging of Betelgeuse, the nearest well-studied red supergiant, has revealed the presence of large-scale surface structures consistent with giant convective cells. The surface of Betelgeuse is not smooth or uniform. It has bright spots and dark regions that shift over time as the convective cells rise, cool, and sink back into the interior. The surfaces of the largest red supergiants, at 1,000 or 1,500 solar radii, are presumably even more extreme in their convective structure. Vast, slowly churning, dimly glowing seas of plasma where individual convective upwellings are larger than the entire solar system. Let's end where the science leaves off and the imagination begins. The question of how large a star can be has a theoretical answer and an observational answer. The theoretical answer is approximately 1,500 to 1,800 solar radii, based on the physics of stellar evolution and the dynamics of very large stellar envelopes. The observational answer is approximately 1,500 solar radii, based on the most reliable current measurements. The two answers agree, which is reassuring. It suggests that we are seeing stars near the physical limit, rather than being limited by our observational capabilities. But astronomy has a history of limits being revised. The physics of stellar evolution has become more sophisticated over decades, and models that seemed robust have been updated as observations revealed new complexities. The behavior of stellar envelopes, convection, and mass loss in the most extreme red supergiants is not fully understood. The boundary between stars that become red supergiants and those that become other types of evolved objects is not perfectly characterized. And the observational coverage of the Milky Way remains incomplete. The inner galaxy, the densest, most heavily obscured region, contains the highest concentration of massive stars and massive star clusters. Surveys of this region in the infrared, where dust is more transparent, have been expanding in recent years. The discovery of RSGC-1 and its extreme members is itself a consequence of such surveys. As infrared surveys of the inner galaxy become more complete, it is virtually certain that additional populations of red supergiants will be found, and the probability of finding an object exceeding current record holders will increase. The Nancy Grace Roman Space Telescope, scheduled for launch in late 2026, will conduct near-infrared surveys of the galactic bulge and inner disk with a combination of wide field and resolution that has not been available before. Roman will detect millions of individual stars in the most obscured parts of the galaxy, and among them, the most extreme red supergiants that currently hide behind curtains of dust. Whether Roman will find a star larger than RSGC-1, F01 is uncertain. But the probability that the current record is also the absolute record, that the largest star we have measured is truly the largest that exists in the Milky Way, is essentially zero. The galaxy is simply too large and too incompletely surveyed for that to be likely. The title of the largest star is almost certainly held by a star we have not yet found. There is something philosophically striking about this entire story that deserves acknowledgement before we close. The Sun, which has powered life on Earth for 4.6 billion years, which drives every weather system and every ecosystem and every photon of energy that has ever fed a living thing on this planet, is a relatively modest star. Compared to the record holders we have discussed, it is a point, essentially negligible in size. And yet the Sun is itself, by human standards, incomprehensible. Its diameter is 109 times Earth's diameter. Its volume is 1.3 million times Earth's volume. Its mass is 333,000 times Earth's mass. The largest red supergiants make the Sun look like a marble makes a grain of sand look. The scaling is so extreme that even the analogy breaks down. At 1,500 solar radii, a star's surface area is 1,500 squared, 2.25 million times the Sun's surface area. 2.25 million times the area of something that is already 1.3 million times the volume of the Earth. The universe produces objects of this scale. Not rarely, not in extreme corners of the cosmos, in our own galaxy within a few thousand light years, in places we can observe with infrared telescopes from the surface of the Earth. Objects so large that the entire concept of stellar scale needs to be redefined multiple times to accommodate them. The night sky, from our perspective, shows these stars as points of light, some of them colored, some of them brighter than others, some of them varying subtly in brightness. Nothing in their appearance suggests the extraordinary physical reality they represent. Antares, visible on summer evenings, a reddish point of light in Scorpius, 680 solar radii. The inner solar system submerged, Mu Cephei, a point of crimson light in Cepheus, 1,000 solar radii. Mars and the asteroid belt swallowed. The stars at the edge of our catalogs, RSGC-1F01, WHG-64. Invisible to the naked eye, buried in infrared bright clusters behind dust, detectable only with modern instruments. 1,500 solar radii, Jupiter's orbit submerged, and somewhere out there, undiscovered, perhaps larger still. The universe does not announce its most extreme objects. It hides them in dust, reveals them only to those who look with the right instruments, and revises the record every time the instruments improve. The search for the largest star is not finished. It has barely begun. As you drift towards sleep tonight, somewhere in the galaxy, a red supergiant is quietly expanding. Its outer layers, moving at speeds too slow to be perceptible over human lifetimes, are pushing outward against the radiation pressure from within. Over thousands of years, it will reach its maximum extent, and at that maximum, it may be the largest object in the Milky Way. We do not know its name. We have not yet observed it. It may be hidden behind a dust cloud in the inner galaxy that no current survey has penetrated in sufficient detail. It may be in a cluster we have cataloged but not fully analyzed. But it is there. The physics guarantees it. In a galaxy of hundreds of billions of stars, some fraction are massive, some of those massive stars are in their red supergiant phase, and among those in their red supergiant phase, some are near their maximum extent. The largest star in the Milky Way is out there right now, vast, dimly glowing, slowly losing mass into the surrounding space. Decades or centuries or millennia from the end of its supergiant phase, after which it will either explode or collapse or contract to something smaller. We will find it eventually. The instruments are improving. The surveys are expanding. The algorithms that search through infrared catalogs for extreme objects are becoming more sophisticated. When we find it, it will revise the record. It will give us another size comparison to contemplate, another reference point that makes everything familiar feel small. And then, after enough time, we will find something larger still. This is the pattern. This is how science moves. Each generation of instruments reveals what the previous generation could not see, and what it reveals is always more extreme, more complex, more far from intuition than what came before. The universe is not bound by our imagination of it. It is bound only by its own physics. And its own physics, it turns out, is capable of producing stars that would swallow Jupiter. For those still awake as the last edges of consciousness dissolve, my biggest goal on this channel is to reach 1,000 subscribers. So if you enjoy falling asleep to my videos, please hit that subscribe button. We continue. The comparison that perhaps captures the scale most vividly is not the solar system one, not the disappearing planets and the engulfed orbits. It is the light travel time. On the Sun, light takes approximately 2.3 seconds to travel from one side of the Sun to the other, across the full diameter of 1.4 million kilometers at 300,000 kilometers per second. On Vy Canis Majoris, at approximately 1,420 solar radii, light takes approximately 2.3 seconds times 1,420, about 3,300 seconds, or nearly an hour, to travel from one side to the other. On RSGC 1F01, at approximately 1,500 solar radii, light takes approximately 3,450 seconds, about 57 minutes, to travel across the full diameter. An hour for light traveling at 300,000 kilometers per second to cross one star. The same light that takes 8 minutes to travel from the Sun to Earth. The same light that takes 1.3 seconds to travel from the Earth to the Moon. 1 hour to cross a single star. Hold that number in your mind as you drift toward sleep. Not as a piece of information to remember, but as a feeling. The feeling of a universe that produces things on scales that make the ordinary measures of enormous. The solar system, the distance to the Moon, the speed of light feel almost quaint. The universe is not what we imagined. It is bigger. Sleep well.